So there's a certain region in which there is a uniform magnetic field. Okay, uniform and constant also. And you can see there is a rectangular loop here, conducting loop. Initially, the loop is completely inside the magnetic field. Let's say this side is, okay, let's call this as B. Call this side as A. This rectangle, let's say, is moving with a constant velocity V to the right. So in a moment, it will start going out of the magnetic field. At least some part of the rectangle will be out of the magnetic field. So one of you tell me, what happens to the magnetic flux through this loop as it moves to the right? What happens to the magnetic flux through this loop as it moves to the right?
Sir, it will change.
Okay. Why? The field is not varying, no? Why does the flux change?
Sir, as it will pass the boundary, so the amount of flux, like as it moves, it will be less, right? It will become less and less.
Okay. The number of field lines passing through that loop will decrease. Okay. Initially, the complete loop is inside the magnetic field, so there are a lot of field lines passing through it. But as it leaves the magnetic field and comes out, or okay, this same loop, when it goes out a little bit like this, now field lines are passing through only this part of the loop. Okay, so the total number of field lines through the rectangle is now lesser compared to earlier. And as the rectangle moves out further, okay, like when it comes to this position, there is an even lesser area through which the field lines are passing. So the number of field lines inside that rectangle or passing through that rectangle decreases. Okay. Is this clear to all of you? Did you all understand why the flux through this rectangle changes? Okay. So tell me, as the rectangle moves out of the magnetic field, in which direction does current flow in the rectangle? We have visualized how the flux is going to change. Field lines are directed inward as the crosses indicate. Okay. This magnetic field is directed into the plane of the screen. So flux is inwards. And when the loop comes out, you know what happens to the flux. You know whether it increases or decreases. Based on that, you all tell me the current in this loop as it leaves the magnetic field, will it be clockwise or anti-clockwise? I got one answer as clockwise. We'll see. Rishi, on what basis do we decide the direction of flow of induced current? Okay, Pradyun, can you tell? How do we decide the direction of flow of induced current?
Right hand thumbs rule.
What right hand thumb rule do we have for direction of flow of induced current?
Through lenses law, I remember.
Ha. So,
With that, we
yeah, through lenses law. How do we apply lenses law here and find out the direction of flow of current? Okay, Yash, how did you say it is? clockwise?
Sir, I did B cross V, so I got that upper side will be at higher potential. Like we can assume
Okay,
that
you
there's
took.
a battery in the circuit in the loop.
Okay, you did it that way. Fine, fine. Isha, can you tell how to find out the direction of current in this loop? Okay, listen, all of you. Induced EMF tries to oppose the change in flux. Okay, so there are two things that you need to do. You first need to check the direction in which the field is pointed. Okay, through this rectangular coil or loop, the flux is into the screen. Okay, the field lines are passing into the screen. Now the field is not changing, but the area through which the field lines pass is decreasing. So, any of you tell me, as this rectangle leaves the magnetic field, what is happening to the flux? Is it increasing? Is the flux through the rectangle increasing or decreasing?
Decreasing.
Decreasing, sir.
Magnetic flux is inward, means into the screen, and it is decreasing. Okay. So tell me, should induced EMF try to support this magnetic field or oppose it? Flux is decreasing. So should we support this field or should we oppose the field?
We should support it, sir.
We should support it. Means current should flow in this loop in such a way that it produces magnetic field in the same direction as the existing magnetic field. Okay, current in this loop should flow in such a way that it produces an inward magnetic field. And how should current flow to produce inward magnetic field? It will have to flow clockwise. Okay, so as the loop leaves the magnetic field, there will be a clockwise current flowing in it. Okay, clockwise current produces an inward magnetic field. Now, as the loop leaves the magnetic field, the flux through it is decreasing. This clockwise current produces an inward magnetic field, which will try to keep up the flux without, it will try to prevent it from decreasing. Okay, that is what induced EMF always tries to do. So there will be a clockwise current flowing. Till when will current flow in this loop? See, actually, when it is completely inside, you should not show the current. When it leaves the magnetic field, okay, or at least a little bit is outside the magnetic field, then you can say current will be flowing in it. Till when can you observe current flow in this coil? Will the current exist forever?
No, sir.
Then
Like it
Sir,
should be
till
in the
we
electric magnetic field.
okay. Someone else was saying something,
no, sir, I was about to say the same thing.
right? See, current will be there. Like you will see current in this coil as long as there is EMF induced in the coil, and EMF will be induced when the flux through the coil changes. So here the coil just started coming out of the magnetic field. So as more and more coil goes out of the magnetic field, you will see the flux decreasing. It will decrease further, decrease further. And when the coil is completely outside the magnetic field, the total flux through the coil now becomes zero because there's no field lines passing through it. There are no field lines. Flux becomes zero and it continues to be zero. So after that, there is no change in flux. And if there's no change in flux, there's no EMF induced, there won't be any current observed in this coil. Okay. Fine. Let's say the loop, rectangular loop, there's only one turn. So I'll just call it a loop. is being pulled with a velocity v to the right. Dimensions are given to you, so you can find out the area. After a time t also, you can find out how much area will be inside, how much area will be outside. Those things can be done. And if you know the area which is inside the magnetic field, you can tell how much flux passes through it. So what I want you to do is, let's say this is the situation at t equal to 0. So at t equal to 0, the rectangle just starts leaving the magnetic field. So I want you all to derive expressions for first thing. Flux through the loop as a function of time. Of course, this will be varying, so there will be EMF induced. Induced EMF as a function of time. If you know induced EMF, divide by resistance, you can tell the current also. Anyway, do this all of you. After a time t, when the loop is still leaving the magnetic field, how much is the flux, how much is the induced EMF? Any answer for flux as a function of time? Okay. See, this is how the loop is at t equal to 0. After some time, it would have gone forward. Let us visualize that situation first. It's moving with a speed v. So can any of you tell me in a time t, how much distance will it move if it is moving with a speed v? Eh? An object moving with a speed v covers how much distance in a time t? One of you tell me how distance, speed and time are related.
So distance will be speed into time.
Huh. So if it is moving with a speed v, how much distance will it cover in a time t?
dv, sir. Like v into d.
V into t. Okay, speed into time. Huh. So at t equal to 0, it was the edge of the rectangle was just at the boundary. Then at time t, I'll write it here. It would have moved forward by a distance, speed into time Vt. If it has moved forward by a distance Vt, then that length of the rectangle will be outside the magnetic field now. Then one of you quickly tell me what length of the rectangle will be left inside the magnetic field.
A minus Vt, sir.
Total length A minus the length that has gone out, Vt. That length is still inside the magnetic field and the width B remains as it is. So the area which is still inside the magnetic field, how will you express that? That area as a function of time will be the length which is still inside the magnetic field multiplied with the width. That's all. That's the area that is still inside the magnetic field. Multiply that with the magnetic field, you'll get the flux. Now see, flux is B dot A. It's a uniform magnetic field. Area is also a flat surface here. Okay, so we can easily find out the flux B dot A. B is into the screen. The rectangle is on the plane, in the plane of the screen. That means its area vector will be perpendicular to the screen. Means magnetic field and area vector are in the same direction. So B dot A, BA cos theta simply becomes BA. So flux here as a function of time will be magnetic field B multiplied with the area as a function of time. So capital B into AB in, okay, A minus Vt into B. That's all. Magnetic field multiplied with area to which the field is passing. That is flux as a function of time. Differentiate that, you will get induced EMF as a function of time. Faraday's law. Derivative of this. Now capital B, small b are constants. We'll put it aside. Multiplied with derivative of A minus Vt with respect to time. What is the derivative of A minus Vt? A is a constant. Quick. What is the derivative of A minus Vt, where A and V are constants? Time t is the only variable. What is the derivative of A, which is a constant?
Once.
Derivative of constant, why will it be 1?
So 0, sir. 0.
Derivative of A is 0 and derivative of Vt with respect to time will be V itself, the constant. So this result will be minus capital B small b, and derivative of A is 0. Derivative of minus Vt is minus V. Minus minus cancel. The answer will be capital B small b into V. Okay. Or if you take the width of the rectangle as L, then it will be BLV. Is this clear to all of you? Any doubts in this? So we first imagined the rectangle moving with a constant velocity V. As it moves with a constant velocity V, you see some part of the rectangle going outside the magnetic field. Then the area through which the field lines actually pass will be shrinking, it will be decreasing. And the area through which the magnetic field is passing is decreasing, means the flux will be decreasing. So there will be an EMF induced and all. So first we derived an expression for the area that will remain inside the magnetic field after a time t. Then multiply that with the magnetic field, we get the flux. Okay, differentiate flux with respect to time, Faraday's law, that will give you the induced EMF. Okay. They can ask you to draw a graph of this. Yeah, such questions can be given. Induced EMF, we see that it is independent of time. So it will be constant. But till when? Till the loop completely leaves the magnetic field. Once it completely leaves the magnetic field, the flux becomes zero and continues to be zero, means flux becomes constant, EMF becomes zero. So as the loop is leaving the magnetic field, all these will be observed. Right. Now try to answer this question. There's a boundary here. Below that boundary, there is a uniform magnetic field directed into the plane of your screen. Uniform and constant also. But it's only below that boundary, not above it. Okay, it's a horizontal boundary. And let's say you release a metallic loop. Okay, so consider gravity also. There is a metallic loop in the vertical plane. Gravity is in the downward direction. We release the metallic loop. Now, see, as long as the magnetic field is not present, gravity will be the only thing acting on it. It will fall with an acceleration equal to g till it reaches here. Till it enters into the magnetic field, it falls with an acceleration equal to g. I want you all to tell me what happens after it enters into the magnetic field. Will the acceleration continue to be g? Will it become less than g or more than g? And why? So I'll write the question here. What happens to its acceleration after it enters the magnetic field? Try this, all of you. Okay, can any of you comment on what happens?
Sir, I think the G decreases.
Okay, you should not say g decreases, you should say acceleration decreases. Why?
Sir, because there's like a force acting on it, like on the metallic loop, there's like a force acting on it. So, and it
Wait.
obviously would stay due to
Which force is acting?
like the magnetic force acting on it.
So when it enters into the field like this, okay, why do you think a magnetic force acts on a metallic loop? And in which direction is that force? Anyone? The moment it enters into the magnetic field, it will have some velocity. It would have gained a little bit of velocity by then. What does the magnetic field do to the loop?
So as this loop enters,
Hmm.
the flux will change, so EMF will be induced.
Correct. Initially, the loop was completely outside the magnetic field. There was no flux. There was no change in flux also. But as the loop enters into the magnetic field, the area through which the field lines pass increases. Okay. So field lines start passing through this loop now. And as the loop enters further into the magnetic field, more and more field lines pass through the loop. So flux is increasing. Okay. So as the loop enters into the magnetic field, flux increases. External magnetic flux increases. So Yash, tell me, should the induced EMF support this external magnetic field or oppose it?
It should opposite.
It should oppose because the flux is increasing, no? According to Lenz's law, induced EMF always tries to oppose the change in flux. If flux is becoming stronger, the induced EMF will create a field in the opposite direction. Okay. Then there will be EMF induced. After that, what will happen?
Then the current will flow in anti-clockwise.
Okay. See, these field lines, the existing magnetic field lines, they are into the screen. Okay. And as the loop enters into this magnetic field, the flux through the loop is becoming stronger. Inward flux is becoming stronger. So the induced EMF should create an outward magnetic field. And for the magnetic field to get produced in the outward direction, the induced current has to be anti-clockwise. Induced current will start flowing like this. Okay. Then after that, what happens? Or due to that, what happens? Anyone? Why should there be or do you think there will be any force on the loop? If yes, why?
Sir, can I give my answer?
What did you say?
Can I give my answer?
Continue.
Sir, magnetic force on a closed carrying loop will be zero right here.
If the magnetic field is uniform and it's a closed loop, the force has to be zero.
So the acceleration will be g.
Okay. I mean, you misunderstood the idea. Listen, all of you. We had learned that the net magnetic force on a closed current carrying loop in a uniform magnetic field is zero. Now, this loop is not in a uniform magnetic field yet. Okay. As it enters into the magnetic field, the entire loop is not in uniform magnetic field. Here, the magnetic field is non-zero. Here, the field is zero. So, for the loop, the field is not uniform. Okay. At places where the loop is present or over the area which the loop is occupying, the magnetic field is not uniform. Fine. So there will be a force acting on it. And why? I mean, you can justify it like this also. The moment the loop starts entering into the magnetic field, current starts flowing in it. Okay. So now it is like there are current wires inside this magnetic field, current carrying wires inside this magnetic field. The entire loop is not inside the magnetic field, but this part of the loop definitely is inside the magnetic field. And magnetic force will act on that part of the current carrying wire. Can one of you tell me the formula for magnetic force on a current carrying wire?
BIL, sir.
I L cross B. Remember the proper formula, okay, with cross product and all. It is I L cross B. L vector should be taken from the first point of the wire to the last point of the wire on which the force is acting. So in this case, the L vector will be from here to here. This is the L vector. So L vector is to the right. Magnetic field is into the screen. Fine. How did we get L vector to the right? Because current is flowing that way. Current is flowing from here to here. So depending on the flow of current, you draw the L vector. L vector is to the right, magnetic field is inward. Then if you do L cross B, it will be in the upward direction. Okay. Which means there will be a force acting on this frame in the upward direction. There will be a magnetic force acting on it on this frame. This way. And that magnetic force is clearly opposite to gravity. So the loop, as it enters into the magnetic field, will not fall with an acceleration equal to g. Okay, it will be falling with an acceleration less than that. Is this clear to all of you?
So can you explain the last part once again?
See, as the loop enters into the magnetic field, the flux through it changes. There will be an EMF induced. There will be a current induced. That much did you understand?
Yes, sir.
Now, the loop is still entering into the magnetic field. It's not completely inside. Now, the part of the loop which is inside the magnetic field, it carries a current, so it will experience some force. And the part of the loop which is inside the magnetic field is not closed. The entire loop, if you see, it's a closed object. But the part of the loop which is inside the magnetic field, which I have highlighted in orange, it's not closed. Okay, so it's like a current carrying wire inside a magnetic field. Current carrying wire in a magnetic field experiences a force given by IL cross B. And in this case, L vector, that like based on the flow of current, L vector is to the right. Magnetic field given in the problem is into the screen. So L cross B will be in the upward direction. The magnetic force on that part of the wire will be in the upward direction. So the loop will not enter into the magnetic field with an acceleration equal to g. It will enter with an acceleration less than g.
Oh, okay, sir. Understood. So, sir, I have a doubt. So,
What is
so
it?
when the whole metallic loop is inside the magnetic field, will the acceleration be equal to g or less, more than g?
Okay. Try to answer this, all of you. Once it is completely inside the magnetic field, then how will it fall? Will it fall with an acceleration equal to g, less than or greater than g? When it is completely inside the magnetic field, tell me, will it have induced current or not? Will there be current passing in that loop or not? I got one answer as acceleration is equal to g. We'll see. But just tell me, when it is completely inside the magnetic field, will there be any net current in that loop or not?
Also,
No, sir.
Why not?
Because the magnetic field is uniform and
The
it's
field is
supposed to be zero.
uniform and the entire area is filled with the magnetic field. So there is flux through the loop, but that flux won't change. And if flux won't change, there won't be EMF induced, there won't be a current. If there's no current, there's no magnetic force at all. Only gravity will be acting on it. It will fall with an acceleration equal to g. Rishi, is this clear?
Yes, sir. Yeah.
Okay. Okay. Right. Any doubts in this? Fine.
sir, I have a doubt.
What is it?
If we imagine that magnetic field is very big, like the area occupied is very big,
I didn't understand.
like the volume occupied by the magnetic field here is very big compared to the loop.
Okay.
So if we now leave the loop, will it achieve a terminal velocity?
Why will the loop achieve terminal velocity? Once it enters into the magnetic field completely, the magnetic force disappears, only gravity will be acting on it. When there's no opposing force, why will it achieve terminal velocity?
Yes, got it.
Hmm. Consider this, all of you. Suppose this is a metallic frame. It's in a uniform magnetic field. Magnetic field is directed into the screen. Suppose there is a rod like this. That rod is also made of metal. So that rod is movable. It's not fixed to the metal. So effectively what you get here is a loop. But it's not a loop of fixed dimensions. As the rod moves forward or backward, that loop's area can be expanded, it can be contracted, it can increase and decrease. Okay. Suppose the magnetic field is uniform and constant. And you give this rod some velocity, let's say a speed u to the right, and release it. And okay. Assume there is some resistance only here. The other rods, wires, they are all like ideal conductors. So we give the rod some velocity u to the right and release it. What will happen? I mean, will the rod continue moving with that velocity? Will its velocity increase, decrease, why? And what happens later? Think carefully and answer. Okay, Yash, what do you want to say?
So like as this rod is moving, it is in contact with the rail, right? Metallic frame.
It is sliding on that metallic frame, yes.
So the leftmost part, it will form a loop, sir.
On the left side, clearly we see a closed loop. Yes, it's a conducting loop.
And as it is moving to the right, the area will be increasing. So area will be increasing. So flux will change.
Okay. As the metal rod moves to the right, okay, let us name the rod as AB. As AB moves to the right, we made it move that way, okay? The loop's area expands. So the number of field lines passing through it will increase, flux increases, EMF will be induced. Okay. Continue. Yes, continue.
And then, sir, we can find the direction of induced current.
Tell me the direction of induced current. See, I hope this is clear to all of you. As the rod moves to the right side, the area enclosed by the loop increases and magnetic field will be present in that entire area. Okay. So the flux is increasing. Okay. So, yes, tell me what should be the direction of induced current in that loop?
It should be anti-clockwise.
Anti-clockwise. The existing magnetic field is into your screen and the flux is increasing. So induced EMF will produce a field in the opposite direction. Induced EMF should produce a field in the outward direction, means the current should flow anti-clockwise. Okay. As a result, what will happen to the rod? Someone else tell me, if that rod now has a current I passing through it in the upward direction, as you can see, and you know there is a magnetic field directed into your screen, what happens to that rod? It's a current carrying conductor in a magnetic field. What does a magnetic field do to a current carrying conductor? It exerts force on it. Okay, IL cross B. Now you look at the conductor AB, current is flowing in the upward direction. So the length vector is this way, L vector. B is into the screen. So IL cross B. Can one of you tell me the direction of IL cross B there on the rod AB?
So it will be towards left.
It will be directed to the left. Okay. So effectively what will happen, because of the magnetic force or because of the current flowing in it, there will be a magnetic force acting on that rod this way. And what will that magnetic force do? It is opposite to this velocity. So it will slow down the rod. Fine. So the speed will decrease. Eventually, what do you think will happen? Will the rod stop? Will it come back? What do you think will happen? We know it is going to slow down. It will continue slowing down. It will stop. After that, will it come back or not is the question.
Sir, it will stop.
Okay. Why will it not come back?
Sir, to come back, it should need a force in the leftward direction, right?
Magnetic force is there, no? Will it not be there? Okay. See, the moment it stops moving forward, okay, let's say somewhere ahead, the speed of that rod becomes 0. Assume somewhere here the speed becomes 0. Then when speed is 0, the area will not expand anymore. Rate of change of area will become 0. If rate of change of area is 0, rate of change of flux is 0, induced EMF will become 0. Current will stop. Okay. So as the rod slows down, the rate at which area expands will also decrease. Area will be expanding. Okay. As the rod goes from here to here, the area expands. But initially, area will be expanding faster because the speed is more initially. But as the rod slows down, area won't expand that fast. Means the rate of change of flux won't be that high. Means the induced EMF won't be that high. Means the current won't be that high. Current will decrease. So speed decreases, current decreases, both will become 0 at one point. Okay. After that, there's no reason why the rod should move back. Okay, it will not. Is this clear to all of you? Any doubt in this? Okay. Actually, we can frame many interesting questions out of these. In place of resistance, if you put a capacitor, no, something interesting will happen. like if it's a charged capacitor, it will try to get discharged. Okay, then there could be current in the reverse direction. Such things could happen. We'll discuss those situations later. Okay. So the three questions that we have discussed today, I mean, they were all about what happens to a particular object as it enters, leaves, moves in a magnetic field. Okay. Now see, according to Faraday's law, when the magnetic flux through a conducting loop changes, loop or a coil, okay, magnetic flux changes, EMF will get induced. That is what Faraday found out. Okay. Now, flux is a quantity which depends on magnetic field, it depends on area, and it depends on the angle between field and area, orientation between them. So if you want to change flux through a loop or a coil, you can change the magnetic field, you can change the area, you can change the orientation, you can change these two, you can change these two, you can change all three also. Right? So by varying one or more of these three terms, the flux can be changed. Flux through a coil can be changed. And when flux changes, EMF will be induced. This is the idea behind the working of a generator. So you do something and change flux through a coil, it will produce EMF. You do something and change the magnetic flux through a coil, it will produce EMF. And that EMF can be used to produce current. Okay. So we will now discuss why a change in flux induces an EMF. Okay. There are several methods to change flux, as we have just discussed. You may change the magnetic field, you may change area, you may change the orientation between them, or you can change two or more at once also. Okay. Now see, if you want to change the area of the loop or the orientation of the loop, these two things involve movement of some part of the loop, some part or whole of the loop also. Okay. In a magnetic field. Okay, if you want to change area, let's say you want to expand the area of a loop, you'll have to move some parts of the loop, right? If you want to decrease the area also, you'll have to do something like that. If you want to change the orientation, you'll have to, you can rotate the loop inside the magnetic field. So changing the area or changing the orientation involves the movement of some or whole of the loop inside the magnetic field, and the loop is a conducting loop. So it means that moving a conductor inside a magnetic field should somehow be generating EMF. Okay, because changing area or changing orientation is producing EMF, means moving a conductor is producing EMF. Okay, and that is what we call as motional EMF. Basically, EMF generated when a conductor moves inside a magnetic field. Okay. Let's see why this has to be generated and how much EMF will be generated when conductor moves inside a magnetic field. Imagine there is a uniform magnetic field directed, as usual, into the plane of the screen. Okay, conditions are very important. The formula we derive in one situation need not be applicable in another situation. Okay, so you need to understand the conditions that we took when we derived the formula. So let's say the magnetic field is this way into the screen, so it's in the k cap direction or the z direction. Fine. Now consider a conductor along the y-axis. Assume its length is L. Again, we have taken conductor in the y direction. So you'll understand the direction also matters. Okay. and assume this conductor is moving in the x direction with a speed v. So magnetic field is in the z direction, length is in the y direction, and velocity is in the x direction. Means we have taken all three mutually perpendicular to each other. We are taking a particular case now. Okay, just to understand why there will be EMF produced when conductor moves in a magnetic field. Okay, so the case that we have taken here is the case where magnetic field, the length vector, and the velocity vector are all mutually perpendicular. Fine. Now see, this is a conducting rod. Any object will have atoms inside it, will have protons, electrons, neutrons inside it. What is the difference between a conductor and an insulator? Difference between conductor and insulator.
So conductors will have free electrons inside it.
Conductor has electrons which are free to move around. Right. Now, when this conductor moves inside the magnetic field, the electrons inside it and the protons inside it are moving in this magnetic field effectively. Electrons and protons are charged particles. When charge moves in a magnetic field, it experiences a force. Right? Can one of you quickly recollect and tell me what is the formula for force experienced by a charge moving in a magnetic field? Force on charge Q.
Q into V cross.
Q V cross B. Correct. Now in this case, we have taken velocity to the right. Magnetic field is taken into the screen. Then one of you tell me what is the direction of V cross B now? Direction of V cross B.
Upwards.
Upward. Okay, V is to the right, B is into the screen. So V cross B is in the upward direction. Now, if charge is positive, okay, let me write it here. V cross B here is upward. Okay. So if the charge is positive, then the force will be in the upward direction. But if the charge is negative, force will be in the downward direction. Now, protons are positively charged, so they will experience a force upward. Electrons are negatively charged, they'll experience a force downward. And the magnitude of charge on proton and electron is the same. So net charge on this conductor will be zero. Net charge is zero. Net force on this conductor also will be zero. Protons will experience force in upward direction. Electrons will experience force in downward direction. Net force is zero. But there are some electrons which are free to move inside this rod, inside this conductor. Protons are not free to move. They are fixed inside the nucleus. Okay. These are solid objects. So nucleus is not allowed to move around. Protons cannot move. All electrons also cannot move. Some electrons can move. Fine. Negative charges experience force in the downward direction. As a result, what you will see is electrons getting deposited at this end of the rod. The rod was electrically neutral initially. If electrons prefer to take one side, then automatically protons will be left unbalanced on the other side. So charge separation occurs inside this rod. Due to what? Due to the magnetic field. Due to the magnetic force, you can say. Okay. So there is a separation between positive charge and negative charge. If there's a separation between charges, there will be an electric field developed. And generally, as you know, electric field is directed from positive charge to the negative charge. So there will be a field directed this way inside the rod. And if electric field is there is potential difference. That potential difference is what we call motional EMF. Fine. When a conductor moves inside a magnetic field, the magnetic field forces a charge separation inside the conductor. And that charge separation creates an electric field or a potential difference, you can say. That potential difference created is what we call as motional EMF. So let's say the positive charge accumulated here is plus Q. Negative charge accumulated here is minus Q. Okay. Again, I would like to remind you that we took a convenient case here. Magnetic field was into the screen. Velocity was in the x direction. Length was in the y direction. And if you see, charge separation happens in the y direction only because force acts along the direction of V cross B or exactly opposite to it. Now V cross B will be perpendicular to both V and B. If velocity is in x direction and magnetic field is in z direction, then this cross product will either be in the positive y or the negative y direction. And we took the length of the rod conveniently along that direction. Okay. Later we'll discuss what happens if the rod is tilted and all. What if velocity is not in the x direction? All those cases also we'll discuss. But remember that we are taking a convenient case for now. Okay. We have to derive an expression for the potential difference that is developed now. How much EMF is produced is what we need to find out. Can one of you tell me the relation between electric field and potential difference? Relation between electric field and potential difference. Okay. E is equal to minus dou V by dou R. Okay. Potential gradient gives you the electric field. Rate of change of potential difference, or no, I should say rate of change of potential with respect to distance or with respect to position is the electric field. If the electric field is uniform, you can write potential difference delta V is electric field multiplied with the distance. That is the idea we are going to use to derive the EMF generated in this case. But for that, we need to know how much electric field is generated. Now listen. First tell me, what is forcing the charge separation here?
So the potential
No. What is making the charges get separated first of all inside that conductor?
motional EMF.
No. What made positives to go one side and negatives to come to the other side?
Magnetic fields.
The magnetic force acting on the charges. Okay. The magnetic force on the charge, let's say the charge is Q, is QV cross B. So you can say it is QVB sine theta actually, or QV perpendicular B. You can take it like that. Okay. In this particular case, velocity is already perpendicular to magnetic field because we took velocity in the x direction, magnetic field was in the z direction. So you can say that the force on the charges is QVB itself. In this case, I'll put a star here. Okay. This force makes the charges separate. But positive charge and negative charge, naturally they tend to attract each other. Okay. That force of attraction is Coulomb's force. Electrostatic force of attraction between positive charge and negative charge. So QVB is trying to separate them. Electrostatic force Q into E is trying to bring them back together. So when the charges finally settle, when a particular amount of charge separation happens and it remains like that, you can say that this force should be balanced by the electrostatic attraction between the charges. So you can say that the electric field generated here is VB, where V is the speed with which the rod is moving and B is the magnetic field. But again, conditions apply. This is true only for this case. That is the electric field. And the electric field extends from the topmost point of the rod to the bottommost point of the rod. It extends over the length L. So you can say that the potential difference developed across the rod is equal to the electric field multiplied with the length, which becomes VBL or BVL as most books write it. Okay, but again, this comes with a condition. But we are getting somewhere. We are slowly deriving the formula for motional EMF. In this particular case, this much amount of EMF will be induced, BVL. Okay, B is a magnetic field, V is the speed with which the conductor moves, L is the length. But we took a case where magnetic field, velocity and length were all mutually perpendicular. Okay, is this derivation clear to all of you? Okay, if you have any doubts, you can ask. Now see, suppose the rod was tilted or all three like magnetic field, velocity and length were all not mutually perpendicular. Then what you need to do is you need to take their mutually perpendicular components. For example, we started with the force, right? F is equal to, the actual formula for force is Q V cross B. Okay, magnitude, if you see, it becomes Q V B sine theta. You can write it like this also, Q into V multiplied with B perpendicular, or you can write it as Q into B multiplied with V perpendicular. So take magnetic field as it is and component of velocity perpendicular to magnetic field. Why should you take component of velocity perpendicular to magnetic field? Because for cross product, that is what matters. Okay, that's how magnetic force acts. That's how it behaves. So keep the magnetic field as it is and take velocity component perpendicular to it. Or you can do the other way also. Keep velocity as it is and take magnetic field perpendicular to velocity. You have to take mutually perpendicular components. Okay. Then see, for the cross product, mutually perpendicular components of V and B matter. Once you evaluate this cross product, you get the force, no? The force which depends on this cross product is perpendicular to both of them. Okay, generally A cross B, the cross product is perpendicular to both the vectors A and B. So this force is perpendicular to both velocity and magnetic field, and separation occurs along that direction of that force. Okay, so length vector has to be perpendicular to both velocity and magnetic field. Along that direction only the charge separation will occur, and along that direction only the EMF will be produced. Okay, so if you want to find out the motional EMF in a general case, you can take it like this: B, V perpendicular, L perpendicular. Okay, keep one vector as it is. Which one vector? There are three vectors, no? You have choice. Magnetic field is there, velocity vector is there, length vector is there. Take any one of them as it is. Then the second one, take its component perpendicular to the first one. And the third one, take its component perpendicular to both first and second. That way you have to take the components. Then you will always get the correct answer for motional EMF. And there is a mathematical way also to do this. Suppose you are given three vectors and you have to multiply their mutually perpendicular components. Okay. Do any of you know, have you studied vectors in 12th class? The mathematical way to multiply only the perpendicular components of three vectors. Okay, listen. There's something called triple product, scalar triple product. Triple product means three vectors will be multiplied. Scalar triple product means the answer will be a scalar. Okay. So suppose A, B, and C are three vectors. The scalar triple product between them, there is a symbol also for it. I don't remember, but it's taken like this: A dot B cross C. Okay. B cross C, cross product will give you a vector. Okay. A is also a vector. But vector dot vector, the final result will be a scalar. That's why it's called a scalar triple product. Now, how does it give you the product of three mutually perpendicular components? Let us see. First, B cross C. B cross C automatically will give you B multiplied with C perpendicular or C multiplied with B perpendicular. Cross product takes perpendicular components only. Automatically you will get perpendicular components out of it. And the direction of B cross C, okay, this vector direction will be perpendicular to both B vector and C vector, right? And then what are you doing? You are taking A's dot product with this. Dot product takes parallel components. Okay. Now you are doing A's dot product with B cross C vector. For example, what I mean to say is, suppose this is B vector, suppose this is C vector. Okay. You have to imagine this in 3D. C vector is into your screen. Then B cross C will be in the upward direction. B cross C. It's perpendicular to B, it's perpendicular to C also. Okay, it's in the upward direction. Okay, let me try it properly. Okay, now there is a third vector A, something like this. You are taking dot product between A and B cross C. If you are taking dot product between A and B cross C, dot product involves parallel component. Means you will be taking A's component in this direction. A's component in this direction automatically becomes perpendicular to B and perpendicular to C. That way, the scalar triple product A dot B cross C, if you multiply three vectors like this, you will ensure that you are multiplying their mutually perpendicular components. Okay. Someone asked me if it is what is called as box of three vectors, box product. I don't know the exact name. We call it scalar triple product. There's another triple product called a vector triple product, but scalar triple product does this. And another interesting thing is the order does not matter. Okay, you take the magnitude of the scalar triple product. It doesn't matter which two vectors you are taking in the cross product and the third, which one you are doing dot product with. Okay, so this will be same as B dot A cross C. In mathematics, I think you have theorems also proving this. So you can rearrange the vectors, doesn't matter. Finally, you take the magnitude, you'll get the EMF. So to get motional EMF, which three vectors are important? The magnetic field vector, the velocity of the conductor, and a length vector. Okay. Now length vector, it's a tricky thing. You will be given a conductor. From where to where you have to take the length, that depends on the problem. Between which two points you want the EMF, between those 2 points you have to take the length vector. Okay, we'll solve problems, you'll understand. But to calculate motional EMF, you can do this. You can take B dot V vector cross L vector. Or you can interchange the vectors also, doesn't matter. This thing's magnitude will always give you the induced motional EMF. Okay, or generally, or simply if you want to remember the formula, you remember it like this: B, V perpendicular, L perpendicular. All three mutually perpendicular components should be taken. Then you will always get the correct value of EMF. Okay, let's solve some simple problems based on this. So we took this case where the conductor, the rod, was in the Y direction. It was moving in the X direction. Magnetic field was in the Z direction. All three were mutually perpendicular. Okay. Let us change the situation a little bit. Okay, let's say magnetic field is into the screen itself. Let's assign some magnitude to it. Say 2 Tesla. Length of the rod, I assume, is some 5 meters. And it is moving with a velocity (10 meters per second). Okay, its orientation is along the y-axis, but it's moving this way. Okay, somewhere in the xy plane it is moving. at an angle 37 degrees. Okay. Let us name the ends of the rod as X and Y. Calculate the potential difference between X and Y. So basically you have to find out the EMF induced. Try this, all of you. I want answers from all. Magnetic field is given, direction is given, length, direction is given, velocity, direction is given. Find out the induced EMF. I got one answer as 60 volts. We'll see. Rishi, can you unmute? We'll discuss.
Yes, sir.
What are you trying to do?
Sir, I'm not sure actually. I don't know how to start this question.
What are you asked to calculate?
The velocity.
Huh? Velocity is given to you in the question.
Oh yeah, 1 second. Wait, sir, I'll solve it. 1 second.
Okay. Pradyun, what are you asked to calculate?
The change in potential.
See, don't call it change in potential. You have to find out the potential difference between the ends of the rod. Okay, or you can say EMF. What is the only way we know to calculate motional EMF? What formula had we just discussed to calculate motional EMF? Note down the formula, all of you. B dot V cross L, okay, the magnitude of it, or simply B V perpendicular, L perpendicular. Okay. We'll do it in that vector form, and we'll also do it the other way. So one of you tell me how to write this magnetic field as a vector. Magnitude is 2, it is directed into the screen. How to express it mathematically? How do you assign direction to a vector which is directed into the paper or into the screen?
Minus k cap.
Minus k cap. So you can take it as minus 2 k cap. Okay. What about the length vector? Let's take from y to x. It doesn't matter because finally we are only taking the magnitude of that triple product. How do you write the length of this rod as a vector? It's in the y direction.
Five j caps.
5 j cap. Okay. Then the velocity. Velocity is not totally in the x direction. It's in the xy plane. It will have two components. The x component will be 10 cos 37. That is 8 I cap. The y component will be 10 sin 37, 6 j cap. So the velocity as a vector is 8 I cap plus 6 j cap. Okay. Let us use that formula B dot V cross L. L cross V, V cross L. You can put V outside, B inside, doesn't matter. We'll try those combinations also. We'll check if what I said is correct or not. So let's do it this way first. B dot V vector cross L vector. Okay. One of you tell me V vector cross L vector in this case. Eight I cap plus 6 j cap cross 5 j cap. How much does it become? Eight fives is 40. What is I cap cross j cap? I cap cross j cap. Isha, what is I cap cross j cap?
So minus k cap.
No, I cross j is k. It's not minus k. Fine. So this becomes 40 k cap. Let it be. Plus 6 j cap, 5 j cap. If you take cross product, it will be 0. Both vectors are in the j cap direction. Their cross product will be 0. So V cross L, the cross product is 40 k cap. Okay. Now we have to take B dot that. Okay. And then its magnitude. B vector is minus 2 k cap. Dot. This whole thing is 40 k cap. And then you take its magnitude, the answer will be 80 volts. That's the potential difference developed between X and Y. Okay, this is one way. Okay, B dot V cross L. Let us interchange the vectors and see if we get the same answer or not. Let's take V dot L cross B. One of you quickly tell me L cross B this time. L is 5 j cap, B is minus 2 k cap. 5 j cap cross minus 2 k cap. How much will that be?
Minus I, sir.
J cross k is 5
J cross, J cross K is I.
There's a minus sign. So this becomes minus 10 I cap. Correct. Now velocity vector is 8 I cap plus 6 j cap dot. The L cross B vector is minus 10 I cap. If you take the dot product, you will again get minus 80. And if you take its magnitude, it will become plus 80. Okay, so as I said, the order of the vectors does not matter. One vector dot cross product of the other two vectors will always give you motional EMF. Okay, I told you another way also to calculate B, V perpendicular, L perpendicular. Now the magnetic field is in the Z direction. Okay, length is in the Y direction. Okay, which means velocity should be taken in the X direction. So this complete 10 meter per second is not of any use to us. This 8 is what is useful in the calculation of motional EMF. And you multiply all three perpendicular components, 2 into 8, 10 into 5. What? 2 into 8, 16 into 5, 80. That way also, if you simply do, okay, third method, B, V perpendicular, L perpendicular. That way also you are getting 80 volts itself. So depending on the problem, whichever method is convenient, you can choose to use that. So ask me if you have any doubts in this. But don't remember the formula as BVL. Okay. In NCRT, they take that mutually perpendicular case, all three to be already mutually perpendicular. So BVL is useful. I mean, is applicable only in that case. What we derived also is that only. Magnetic field in Z direction, length in Y direction, and velocity in X direction. Then you can use BVL. Okay, but not always. I mean, not in other cases. Generally, this is how you find out motional EMF. So yeah, if you have any doubt in this, you can ask. Okay. Now we found that the potential difference is 80 volts. Which end, X or Y, will be at higher potential? X is the upper end, Y is the lower end. Which end will be at higher potential? Generally, the side to which positive charges go, that will be at higher potential. The side to which negative charges go will be at lower potential. Okay. Now, which charge goes which side depends on the magnetic force, QV cross B. Okay. We had discussed that. Generally, if Q is positive, force will be in the direction of V cross B. So positive charges go in the direction of V cross B. Negative charges go opposite to V cross B. In the given question, velocity vector direction, you can see it's like this. Magnetic field is into your screen. So V cross B, if you take, in this case, it will be this way. Okay, this is the direction of V cross B. So positives will tend to get pushed that way, negatives in the opposite direction. But the rod is not actually in that direction, it's in the vertical direction. Still, you can say that positive charges will go this side, negative charges will come opposite side. So the end X will be at higher potential and the end Y will be at lower potential. So effectively, that rod between X and Y behaves as a battery whose EMF is 80 volts. Okay, is this clear to all of you? And in fact, indirectly, we had derived this in the first problem that we discussed today. You see, this rectangular conductor was moving out of the magnetic field. Okay. So conductor moving in a magnetic field, whatever EMF is generated here must have been motional EMF only. What else will it be? Okay. And see what we indirectly did or unknowingly did. Okay, rectangle has 4 sides. Let's consider each side separately. This side of the rectangle, S1, it's already out of the magnetic field. It can't participate in generation of EMF. Okay. Next, this side of the rectangle, the upper side, S2. Some of it is inside the magnetic field, but if you observe, that side is along the x-axis. Okay, the length of that side of the rectangle is along the x-axis. That conductor lies along the x-axis. It's also moving along the x-axis. So velocity and length are in the same direction. They cannot have perpendicular components. So that side cannot generate EMF. Okay, so motional EMF generated by that side of the rectangle is 0. Similarly, motional EMF generated by the lower side of the rectangle, let's call it S3, that will also be 0 because that rod or that side of the rectangle is moving parallel to its velocity. Sorry, is moving parallel to its own length. So it cannot participate in EMF generation. Why? EMF generation happens due to charge separation by magnetic force. Velocity in this case is to the right. Magnetic field is into your screen. Then V cross B will be upward. In this rod, which lies horizontally, you can't have vertical charge separation. There's no space for vertical charge separation in a rod which lies horizontally. Okay. So in those two sides also, there won't be any EMF generated. Now the last side, this one, its velocity is to the right. Okay. Magnetic field is into the screen. So V cross B will be upward. Positive charges will get deposited here. Negative charges will get deposited here. There is space for charge separation in that rod, in that side of the rectangle. So there will be EMF generated. And that is the EMF for the entire loop. Whatever is the EMF in that side itself is the EMF in the entire loop because the other sides don't have any EMF. Okay. And what is the answer we got? We got the answer as capital B small b into V. Small b was nothing but the length. So indirectly, the answer we got was BLV as expected. Okay. In this case also, the result we derived is BLV only. So generally, when a conductor or part of a conductor moves in a magnetic field causes charge separation inside that conductor. So it generates an EMF in that conductor. And if there is a path for current to flow, current will also flow in that conductor. See, in this rod, okay, if it's only a rod, see, rod is a linear arrangement of molecules. The width of the rod is not considered at all. So if it's only a rod and you move it inside the magnetic field, some charge separation will occur, EMF will get generated, but current won't be produced. It's like a battery which is not connected to anything. How will current flow? Okay, so current will not be produced. But if you complete the loop, then current will flow. Or if you take a thick rod, then current will flow. That's called eddy current. We'll discuss that in coming classes. Okay, so what we effectively discussed today is some cases of Faraday's law. Based on that, how a loop can experience force, okay, due to the current flowing in it, due to induced EMF. Then we started discussing why EMF should get generated first of all when flux changes. Now there are many ways in which we can change the flux. We can change magnetic field, we can change area of the loop, we can change the orientation between them. Whether you are changing area or orientation, that process, those two methods involve the movement of the conductor in the magnetic field. And when conductor moves in a magnetic field, the EMF generated is called motional EMF. Okay. And we derived a formula for motional EMF, B dot V cross L. Basically, you have to take scalar triple product between magnetic field, velocity, and length. So tomorrow I'll send you a worksheet based on this. Next class we'll solve some more problems also. And then we will move on to the other way of generating EMF called induced electric field. Small concept, but interesting concept. And after that, we can talk about inductor, self-inductance, mutual inductance, eddy currents, all those things. Okay, thank you all. We'll continue in the next class. Next class will be on Thursday.